Welcome, 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 my friend, my subscriber, the person that has been following these lessons online and downloading them, sharing them. Whatever you're doing, I'm so proud of you and I pray God blesses you. I want to appreciate the teachers that have always commented, have called me to make these videos better. Thank you so much. Probably some of you have not had enough time to make such videos, but I thank you for your contribution. Thank you for always calling and for always supporting this noble cause. Still Monday, Dennis, Maximus, Zerubbabel, Simon, Peter, Tinoburio. I have many names, and here are my numbers. I just need to remind people that these numbers are registered in my name. Yeah, if you're sending any support, please always double check. You find Monday Dennis. The Maximus bit of it is not there. Yep. And if you want to write to me via email, reach me on dennismandela@yahoo.com, or the first number, which is the empty number, is available on WhatsApp, so we can communicate. So we are still continuing with our waves, and this is part 4. In part 4 we're going to look at diffraction and interference of waves. So let's dive straight into it. So let's start with the diffraction of waves. Now, diffraction is a spreading of waves when they pass through an opening. That is the first case that we have to know, that diffraction is said to have taken place when waves spread when they pass through an opening. Or, on the other hand, diffraction is also the bending of waves around barriers in their path. So you can combine the two. You can say diffraction is a spreading of waves when they pass through an opening, and the bending of waves around barriers in their path. That will be more complete. So if you just state it either way, still you'll be marked correct. Okay? So when a wave is diffracted, there are basically things that you have to consider. Number one, the speed remains unchanged. The speed of that wave remains unchanged. The frequency remains unchanged. The wavelength remains unchanged, but only the direction will change. So only the direction changes, and the change of the direction is always indicated by the change of the shape of the wave fronts. They may be circular and they become more circular, or they may be plain or straight, and then they end up circular or slightly circular at the ends. So as we shall see. So the extent or the degree of diffraction depends on basically 2 factors. But here we're saying the extent or the degree of diffraction depends on the size of the opening. On the size of the opening, there has to be a D here. Sorry about that, please. Sorry about that. I'm gonna put it here. Okay. Here there is something missing here in this space, around here. Oh, sorry for that. The color I'm using isn't visible. I'm gonna use a pen. Yes. So here. So you put it up. Right there, like that. So we are saying that the extent of diffraction depends on the size of the opening relative to the wavelength of the wave. So these 2 factors, which are the size of the opening or the size of the hole or the slit, and the wavelength of the wave, they depend on each other. So they are relative, or they are taken not independent of each other, but they depend on one another. All right. Let me just remove this. So we are saying that diffraction also depends, the extent of diffraction also depends on the size of the obstacle placed in the path of a progressive wave. Remember, we say that diffraction is also the bending of waves around obstacles or barriers placed in their path. So the size of that barrier or the size of that obstacle also determines the extent of diffraction. Please follow me closely, don't go off. Don't go off. These things are very easy. This part is so easy. I know you're going to understand everything. Yeah. So, question. State the factors which affect diffraction of waves. Here is a question and it's for you to answer. You can first pause, you answer. Okay? Pause now and answer that question. Oh, I got an answer for you. There is an answer you can compare with yours. So, the first factor is the wavelength of the wave. Wavelength of the wave. Factor number 2 is the size of the opening. The size of the opening, or you can call it the size of the hole, size of the slit, size of the gap. Opening, gap, slit, hole. Yeah, same thing. And on the other hand, even the size of the obstacle placed in the path of the wave also determines the extent of diffraction. Now, the common two are the first ones here, the first two. Because in most books, people look at diffraction as only limited to the spreading of waves when they go through openings. But then for this case, you also have to know that if there is an obstacle placed in the path of any progressive wave, there will be always the bending around that obstacle. So note, the longer the wavelength, the greater the diffraction and vice versa. That means the waves which have longer wavelength are diffracted to a greater extent or more than the waves which have shorter wavelength. And the narrower the opening, the greater the diffraction. That means if the opening is smaller, is narrower, then the diffraction will be greater, the bending will be greater. Okay, let's first close this curtain and look at something, open something new. Diffraction of waves by, now we looked at the two factors. We said that we have basically the most important two. Please put them into your mind, where we say that we look at the size of the opening. So, and number 2, the wavelength of the wave. Now look at this. Part A, if you have a narrow opening, by a narrow opening, this is what we mean. Look at this. You have a wave incident. These are plane wavefronts. Incident onto a barrier. So there is a barrier, but this barrier has a hole. Now, what will happen won't be reflection. The energy will squeeze itself through this space. Remember, waves carry energy. So when this wave is incident onto this barrier that has a hole, the energy will emerge from this hole. What we are saying is, if you have a narrow slit, that means the length of the slit, is what we're calling D. So we have incident wave fronts, but look at this. The size of the hole is what I'm calling D, and the wavelength of the wave is what we're calling lambda. Now, if you really compare these two properly, you realize that D is smaller than lambda. So a slit or an opening is said to be narrow only if it is only if it is smaller or equal to the wavelength of the incident wave. Let me repeat. A narrow opening is one whose size is less or equal to the wavelength. Okay? D is less or equal to lambda. Now, let me illustrate exactly what happens. So we have these incident wavefronts. That's how they came. And then they are striking. They are reaching a barrier that has a hole, and we all understood that this is a small hole because the size of this hole is smaller than the wavelength, the distance between these two successive crests. this is a wavefront and this is a wavefront, and these wavefronts represent positions of crests. So what will happen is that we shall have circular wavefronts emerging from this point here. So this hole is going to act as a source of circular wavefronts. You see that? So that's what has happened. The wave was traveling in this direction, and then you see what has happened. Only this portion here in the middle has not been diffracted. And by the way, remember I said that diffraction does not affect the speed, does not affect the wavelength. That's why the distance from here up to here, from this like between these successive circular wavefronts should be equal to, and is equal to, the distance between these successive plane wavefronts. Next, now what about if you have a big hole, a wide hole? If the hole is wide, what happens? A wide opening or a wide gap is one where D, from here up to here, D is greater than the lambda. You can seriously see that if the lambda is there. This wave is incident, but from here up to here is bigger than the wavelength. So what will happen? Now look at what happens. Oh, interesting. This portion here, oh, let me try to show you what I'm meaning. This portion here, pen, where you? Yeah. This portion here, this one here. That portion there, I've just highlighted it. Do you see that this portion here went through? It just went through and it diffracted. There was no single bending. The bending is only taking place in these portions, this side, this way, and also down this way. Please, when you draw this diagram, don't also put those things in red. No, I'm just illustrating. Show the incident wave and the diffracted wave. But you see that only the bending has taken place at the edges of the hole. So that happens when the size of the opening is big, or when you have a wide opening. Well, from the wave came that way, and then you see there was no diffraction here, so there was diffraction only at the ends. What about if you have a single obstacle, and let's start with one whose length is greater than lambda, is greater than the wavelength? What will happen? So let's look at still here you have wavefronts. Let me change this. Okay. You have wavefronts, plane wavefronts. They're actually traveling. All I'm trying to illustrate is that if you have an obstacle obstructing this upper region here, what will happen? Definitely it will be blocked. No wave will travel this way, but this other portion there will be diffraction here. There will be a bending in that kind of style. You see? There has been a bending that way around this. So if it was sound, and you are behind maybe a door, you'll hear someone talking from the other side because of diffraction. On the other hand, let's still have wavefronts. Wavefronts are incident. Okay, they are traveling, and then you place an obstacle of length greater than the wavelength. You realize that the length from here up to here is greater than the wavelength. So this is what will happen. In this region here, you will get no wave here. No wave here. But you see, the diffraction, there will be a bending until these wavefronts again join up. So in that kind of style. Now, let's take the last case where the length of that obstacle is smaller than the wavelength. So this is what we are having. Oh my God, this is interesting. So here the wave just passes through as if there is no obstacle. If the size of that obstacle is smaller than the wavelength, there will be no diffraction, completely no diffraction. Yes, there will be no diffraction. So just imagine, maybe you are running and then you find a small stone. It cannot make you fall down. Yeah, this is what exactly happens. It's a small stone, very small. Even if you hit it, you may not fall. Yes, you will feel some pain, but you won't fall. So this wave just continues, no diffraction at all. Okay, now what are the effects of diffraction of waves? Number one, we are able to hear sound around corners of buildings or from people speaking from closed adjacent rooms. If someone is in the other room, hey, by the way, do I have someone that side? Sorry, they've gone. So you can hear someone talking from an adjacent room, even when you can't see them because of diffraction. And then shadows of objects, like if you have maybe a shadow of a flag, those shadows are usually less dark or they are grayish at the edges due to diffraction of light. Now, if you look at shadows, they're not entirely black. You say light travels in a straight line. It's true, but then light will bend around because light is also a wave. So there will be bending of light, and that bending is what we call the diffraction, which makes the edges of the shadow to be grayish because some light will reach there. And then sound heard from a car playing music when doors are closed is usually more of the bass than the treble. If you have someone, if you were near a road and someone comes with booming music, most of the times you realize that you only get the bass. You only get the bass of that music which is coming from the car. Yet it may be, yet if they open the doors and you hear properly, it may not just be just the bass only, but it appears as if the bass is too much. The reason is because the sound of the wavelength of the bass sound is bigger and therefore is more diffracted. To us, we can hear it as compared to the treble, which has shorter wavelength. The treble sound has shorter wavelength and is less diffracted. So for it, we don't get it properly. It can easily go in straight lines almost. But now this bass is diffracted more, so we can easily hear it. So you always hear, if there is sound, I'm not good at beatboxing. Let me leave this alone. Okay, close this curtain. Come on. We open another one. I think that's opening a curtain. So applications of diffraction. Where is it used? So diffraction, we have what we call X-ray diffraction. It's used in the study of crystals. You'll find this in A-level, paper 1 of physics. Yes. We have holography, making of holograms, those stationary images that are taken. They are taken using this principle of diffraction. Holograms are steady photographs of light formed as a result of diffraction and interference of light. Here we're just stating, you can do further research. Somebody thinks the description exceeds the O-level content. So permit me just to state many of them. So to send radio waves over long distances, we use the AM radio waves. If you want to communicate, if communication is to be made by radio waves over long distances, they use AM. AM means amplitude modulation. The radio waves, which are the AM, not FM. FM radio waves have shorter wavelength as compared to AM radio waves. As a result, the AM radio waves are diffracted more than the FM radio waves. Let me just show you something here. Very, very basic. If someone lives behind a hill, supposing, and this is a hill, and then there is a house here. There is a house here, and there is a hill. So now if FM radio waves are incident, the FM radio waves, they may come, not real incident, if the FM radio waves are traveling, for them they have shorter wavelength. So what will happen is that they will travel, they will be diffracted less, so they will travel, and therefore this house here won't receive them. Now on the other hand, the AM radio waves, AM, I don't know why I'm confusing these things. The AM radio waves, let me use another color. The AM radio waves, for them, they have longer wavelength. So if the AM radio waves are incident, for them, because they have longer wavelength, they will be diffracted more. So they will be diffracted and they will reach. So they will reach the house here. So you realize that if someone has here a radio with an aerial, a radio receiver with an aerial, they will be able to receive the AM radio waves and not the FM radio waves. Okay, so FM radio waves, AM radio waves, for them they can be diffracted more than the FM radio waves. Reason, AM radio waves have longer wavelength. So we're saying the AM radio waves are diffracted more than FM radio waves around the mountains and through forests. That's why you see here, even when you are here in Uganda, you can easily tune into radio stations of Tanzania. If you change the node, there is where you can switch into AM instead of FM. You change, there is some kind of button which you can switch, or sometimes you just move it around into the AM and then you will tap those waves. Okay, then another application, we have what we call diffraction gratings. Diffraction gratings have about 25,000 thin slits per inch. Just imagine. But just in 1 inch, they put as many as 25,000 slits. And the slits are equally spaced and have equal width. So a diffraction grating transforms an incident beam of light into a spectrum. And the spectra produced by diffraction gratings are useful in studying the structure of atoms and molecules to investigate the composition of stars. Now, my dear students at O level, do you need to have all this in your mind? No. The application is here. Diffraction gratings. That's all. For O level, we don't really ask you a lot. We're just saying state. So it's beyond understanding how the diffraction gratings operate. Is beyond O level. I've just put descriptions here to not leave you in suspense. So owls are able to communicate over long distances because their hoods, I hope this is what they do, are diffracted greatly through forests. And on the other hand, small birds make short wavelength tweets which do not get diffracted easily. Yeah. So communications of owls, you know owls, the sounds that they make, some, I don't know even exactly how they make those sounds, but those sounds have longer wavelength and therefore they are diffracted more through forests and around trees, that they can travel over long distances as compared to birds. There are those that make very small, very short wavelength tweets. I can't try. So I wanted to demonstrate, but it's hard. So those tweets there, they don't get diffracted easily. Now next, diffraction. We are done with diffraction. I want us to look at interference of waves. Interference of waves. What is interference? So interference refers to the superposition of waves of the same frequency having a constant phase difference. Superposition. Superposition is overlapping. You can say overlapping of waves of the same frequency, and they must be having a constant phase difference. So waves of the same frequency, phase difference, and nearly the same amplitude are called coherent waves. Waves of the same frequency, phase difference, and nearly the same amplitude are called coherent waves. So the sources of such waves are called coherent sources. Coherent sources. Now, what's so special about coherent waves? What is so special about coherent waves is that the frequency has to be the same and the amplitude has to be nearly the same. Okay? And we are saying that the sources of such waves are called the coherent sources. Please don't forget that. Now, types of interference of waves, we have basically two. We have constructive interference and destructive interference. Constructive interference is the interference which results into increased disturbance or increased amplitude. So constructive interference occurs when crests overlap with crests, or troughs overlap with troughs, or rarefactions. When I change this one more time, rarefactions overlap with the rarefactions, or compressions overlap with the compressions. So we can summarize this and say that constructive interference is the interference which occurs when coherent waves are superposed in the same phase. So because we are saying in the same phase, it means it is a crest overlapping with a crest. Okay? So constructive interference is the interference which occurs when coherent waves are superposed in the same phase. In a simple way, because sometimes when we use some of these words they confuse students, but in a simple way you can even define constructive interference as the type of interference which occurs when crests of coherent waves overlap. Are you seeing? I'm not really seeing. Have you heard? You see, we are used to the joke about the environment where we say, are you seeing? So I'm saying constructive interference, you can also define it as the interference which occurs when crests of coherent waves overlap. Or you can say when troughs of coherent waves overlap. So they have to be crests overlapping with crests or troughs overlapping with the troughs, and they must be of coherent waves. So let's have a case here. You have a crest and there is another crest, and these are of coherent, they are of coherent waves. So what will result when these two, supposing that here the amplitude is 2 centimeters and also the amplitude here is 2 centimeters. So what do you get? You're going to end up with a big crest of amplitude 4 centimeters. Now, on the other hand, if you have a shorter, if you have another wave, let's take a crest here of a wave whose amplitude is 1 centimeter, overlapping with a crest of amplitude 2 centimeters, what do you get? Now these two may not exactly be coherent, but you see, what matters is that the frequency has to be the same. So if they have the same frequency, they will be overlapping. And what are we going to end up with? We're going to end up with a bigger crest. Now this is 1, but it's upwards because this is a crest and this is also a crest. So you're going to end up with a bigger crest of amplitude 3 centimeters. It's just like saying 1 plus 1 you get 3, 2 plus 2 you get 4. Just like that. Now be careful, if it's a trough we go into the negatives. So destructive interference now is the interference which results into reduced disturbance. It results into reduced disturbance or reduced amplitude. And destructive interference occurs when crests overlap with troughs of coherent waves. Sorry, I didn't put that there. But you can say in other words that destructive interference is a type of interference which occurs when crests overlap with the troughs of coherent waves. Okay, you have crests overlapping with the troughs, and they must be of coherent waves. So you can have rarefactions overlapping with compressions. Now, total destructive interference results into zero disturbance. There the amplitude will be zero, and we shall see exactly when it happens. So let's look at this case. You have a crest and then it overlaps with the trough. Now if the amplitude here is 2 centimeters and also here the amplitude is 2 centimeters, but remember for the trough it's going downwards, so it's like you're saying positive 2 plus negative 2. What do you get? The answer is 0. So you get no disturbance at all, and this is what we call total destructive interference, where there is no disturbance at all. On the other hand, if you have a trough, I'll start with a trough this time, of amplitude 1 centimeter overlapping with a crest of amplitude 2 centimeters, you're going to end up with, now this is negative 1 plus positive 2. What do you end up with? Negative 1 plus positive 2. Definitely you get positive 1. So you end up with a crest of amplitude 1 centimeter. So in a ripple tank, interference can be demonstrated in 2 ways. Number 1 is by using 2 spherical dippers at positions S1 and S2 to produce circular waves which will interfere. On the other hand, you can allow straight or even circular wavefronts to pass through 2 narrow openings close to each other in a barrier. So each opening will cause diffraction and the diffracted waves will interfere. So let's illustrate the 2 cases. Now here, I have a source of circular wavefronts. This source I'm calling it S1. So you have, maybe you can use a spherical dipper, S1, this one here. The source 1. What about if I have another source S2, just not far from the other one, and it also produces circular wavefronts? What will happen? You see what is happening? There is a very interesting pattern. If you look closely, you realize that here, there is some interesting pattern. I think the crossings here, they are in some kind of line. So I will illustrate that later. So at this point, remember each of these wavefronts represents a position of a crest, and then just in the middle here, like for example here there is a trough. This is a crest in between there is a trough, crest in between there is a trough. So I want you to note it properly. Let me talk about the second scenario, then I explain further. So we are saying that these 2 here are the wave sources from ball-ended dippers, or you can call them spherical dippers. On the other hand, we can just use a barrier that has 2 slits. So they have to be of equal size. Those are identical slits, slit 1 and slit 2. Now if you allow straight wavefronts to be incident on this barrier that has 2 slits, what will happen? So for the first barrier S1, we are seeing circular wavefronts produced, and even from the second barrier we are having circular wavefronts produced, and still we end up with our pattern like we had before. Now I want you to note this. I have tried to draw lines here to join these points of intersection where the crest is meeting a crest. Now what did we say is the type of interference that occurs when a crest overlaps with a crest? So we call that constructive interference. Now these lines that join points of constructive interference, those lines are called the antinodal lines. So here we have an antinodal antinodal, antinodal, and antinodal. They are antinodal lines here, the lines of constructive interference. On the other hand, I told you that there's space between here, like at this point here, like just follow what I'm, maybe let me illustrate with some kind of pen, like here in this position where I'm putting these marks here. This is the position of a trough. I see the blue marks, those ones. So that's where troughs are located. Between the two wavefronts, always just right between there you have a trough. Now I want you to look at this. I request you to look at this. Look at this. Do you realize that here there is a crest meeting with a trough? Even here, there is a crest meeting with a trough here, a crest meeting with a trough here, a crest meeting with a trough. You see those points? Crest meeting with a trough, crest meeting with a trough, crest meeting with a trough. Even if you follow this line here, there is a crest meeting with a trough, a crest meeting with a trough, crest meeting with a trough, crest meeting with a trough, crest trough meeting, crest trough overlapping, crest trough superposed, like that. Now, those lines correspond to regions of total destructive interference, or you can just say destructive interference. And those lines are called, can you guess the answer? This was antinodal, and this line was called an antinodal line. What about this one? Don't call it anconodal. This one is called a nodal line. So, for example, here I've labeled this one that is called a nodal line. Nodal line. Yes, write the right spelling. Nodal line. Always pause these videos and draw these diagrams. You just put a compass here, and then you draw those concentric arcs, and then also here you draw those concentric arcs, and then you'll see the pattern coming out. Now the technique is that these ones have to be equally spaced. Please note that. Equally spaced. If you're drawing an arc after every 1 centimeter, maintain that. Okay. Now, in light, constructive interference is observed by bright lights, or what we call the bright fringes, and destructive interference is observed by darker fringes. And in sound waves, constructive interference produces increased loudness, while destructive interference produces quietness or decreased loudness. Now, someone may be wondering, where do we apply interference? What are the applications of interference in normal life? If you have traveled by plane, probably, we have you may be given the noise cancelling headphones, or you may also have your own. You can use them. What those headphones do is that they produce a wave which is out of phase with the wave that they receive, so that it cancels that sound. So when you put those headsets off, they will cause destructive interference of the sound that may be coming from the plane, or that may be coming from any vehicle in which you are traveling. And on the other hand, we have, so planes now, not everyone will be given the headphones. So what they always use is that they use what we call the automobile mufflers. Automobile mufflers, the spelling. Let me try to write it here. Automobile, automobile mufflers. So automobile mufflers, they help to cancel out the sound that is coming from automobiles, and will therefore enable you to stay and to travel comfortably. Now, I request you to look for other applications. Yes, look for applications of of interference of waves.
Jen